Assalamualaikum to Dr. Roshaini. I am Sasha Erinda binti Sahiri.
Hi, my name is Nur Fazilia Atika Safia binti Muhammad Feroz with metric number 0024267236.
My name is Rusna Azmiza binti Nur Azman and my matrix number is 2024282792.
We are from RAS 2134A are going to present about a subtopic of PHY533, which is 6.1. Relationship between the center of mass and the linear momentum of the system. To begin with, I will introduce you to what is center of mass and what is linear momentum. In physics, the study of motion of system consisting of many particles required simplified approaches to describe their overall behavior. There are two fundamental concepts used for this purpose. The first one is center of mass and the second one is linear momentum. The center of mass is defined as the point at which the entire mass of the system can be considered to be concentrated, and it represents the average position of this system's mass distribution. On the other hand, linear momentum is a vector quantity defined as the product of mass and velocity. Product of mass and velocity describe the motion of an object or system. So, this is the simulation of center of mass and linear momentum.
Hi, I'm going to talk about theoretical and derivation. There is centers of mass, linear momentum of the system, relationship between the center of mass and linear momentum of the system, effect of external and internal forces, motion of center of mass. First, I'm going to talk about center of mass. We start by defining the total mass of the system that can be written as capital M. It's the summation of individual particle masses. Next, we also need to know about the position vector. The position vector of center of mass can be written like this. The definition of position vector of the center of mass are the mass weight average of all position vector. Next, I'm going to talk about linear momentum of a system. Linear momentum of the system is a product of mass multiplied with velocity. The linear momentum can be written like this, and other definition of linear momentum is summation of individual momentum. To connect this with the center of mass, we need to cross multiply with the position vector that we can get this. Now, I'm going to talk about the relationship between the center of mass and linear momentum of the system. To observe the center of mass, we need to take time derivative to the both sides to find how it changes over time. As we know, m is a constant value, so we take out from time derivative. Since the derivative of position vector equals to velocity, we can write it like this. By that, we can also simplify the equation to this. Since the right hand side equals to linear momentum, we also can write it as linear momentum equal to mass over velocity of center mass. Next, we're going to talk about effect of external forces and internal forces on linear momentum of the system. A system consists of forces, which is external forces and internal forces that I write for F vector with I in there, F vector with IG in there. Now, let's apply the Newton's second law, which is F equal to ma. As we all know, acceleration equals to derivative of velocity, so we can write it like this. So, we can write the calculation like this. External plus internal equals to ma. Summing this relationship across the entire system will give us this. Next, I'm going to talk about motion of the center of mass. According to Newton's third law, it's equal and opposite. That means this one and this one going to be cancelled out, which lead it to become zero. Due to that, the acceleration also becomes zero. Like I said before, since the acceleration is derivative of velocity, we can conclude that velocity is constant. Therefore, we prove that total linear momentum of isolated system is completely conserved.
Next, I will discuss about a question in the textbook. This question demonstrates the conservation of linear momentum when a ballistic missile breaks into 3 fragments. Before the breakup, the missile has mass of m and a velocity of v0. The missile suddenly breaks into 3 equal fragments, so each fragment has a mass of m/3. The first fragment continues moving in the same direction with the speed of v0/2. The other 2 fragments move at a right angle 90 degrees to each other. These 2 fragments have equal speeds, which we need to determine. Since there is no external forces acting during the explosion, the total linear momentum before and after the breakups remain the same. So we write mv0 equals to m/3 v1 plus m/3 v2 plus m/3 v3. Because every fragment has the same mass, we can cancel the m. Then we can multiply both sides by 3 by obtain 3 v0 equals to v1 plus v2 plus v3. So the next step, we can use the vector relationship. From the diagram, v2 and v3 are perpendicular. Therefore, if we dot product v2 and v3, it will equals to 0. The question also stated that both fragments have the same speed, so v2 will equals to v3. After that, we can substitute the value of v1 equals to v0/2 inside the equation of 3v0 equals to v1 plus v2 plus v3. Then, the equation will become 5/2 v0 equals to v2 plus v3. Next, we can dot product of each side with itself. That means 5/2 v0 with times with itself will become 25/4 v0 square. For the right hand side, v2 plus v3 will times with itself, it will become v2 square plus 2v2 dot v3 plus v3 square, and it will become 2v2 square. For the last step, we have to calculate the speed by solving v2. v2 equals to 5/2 square root of 2 v0. Since v2 equals to v3, we also can get v3 equals to 5/2 square root of 2 v0. Therefore, v2 will equals to 1.77 v0. These are another example of center of mass. The question is, there are 3 particles are located in 3-dimensional space as follows. Then, we have to determine the position vector of a center of mass of the system by using this formula. The first step, we have to find the total mass. Therefore, we have to add all the mass, which is 4 kg, 8 kg and 6 kg, equals to 18 kg. Center of mass at x coordinate, we can determine by the total of product of mass times with x over total of mass. Therefore, 4 times 2 plus 8 times -5 plus 6 times 7 over 18 is equals to 0.56. For y coordinate, we just use the same step, but we just change the y coordinate. So 4 times 3 plus 8 times 4 plus 6 times -2 over 18 is equal to 1.78. The center mass at z, we just change the z coordinate, which is 4 times -1 plus 8 times 6 plus 6 times 3 over 18, and it will equals to 3.44. Hence, the answer for this question is equals to 0.56i plus 1.78j plus 3.44k.
Hi, now I want to talk about application of the relationship between the center of mass and linear momentum of a system. Now, let's look at the first application, which is an aerospace engineering, specifically during the mid-air fragmentation of a missile or rocket. When a missile explodes, the chemical reaction generates internal forces that cause the missile to break into many fragments. However, these internal forces cannot change the total linear momentum of the system. Since there is essentially no net external forces acting on the explosion except gravity, which affect all fragments equally, to the linear momentum remains conserved. As a result, although the fragments fly in the different directions with different velocities, the center of mass continues to follow the same trajectory it would have followed its explosion had never occurred. The principle is very important in aerospace engineering because it helps engineers to predict the motion of debris after an explosion, which is essential for trajectory analysis, safety planning, and defense system design. The second application is firearm recoil dynamics. Before the gun is fired, both of the recoil and the bullet are at rest, so the total linear momentum of the system is zero. When the gunpowder ignites, it creates an internal force that pushes the bullet forward while simultaneously pushing the recoil backward. According to the law of conservation of linear momentum, the forward momentum of the bullet must be balanced and equal, and opposite momentum of the recoil. Because the recoil has a larger mass than the bullet, it moves backward with smaller velocity. This backward motion is known as recoil. Throughout this process, the center of mass of a recoil bullet system remains unchanged since external forces act on the system during the firing process. The final application is in astronomy, particularly in binary star system and exoplanet detection. A star and its planet do not simply orbit each other. Instead, they both revolve around a shared center of mass known as barycenter. The gravitational attraction between the star and the planet is an internal force, so the total linear momentum of the system remains conserved. As the planet moves along its orbit, its momentum is balanced by the star's momentum. This changes the star to move in a very small orbit, creating a tiny motion called stellar wobble. Although this wobble is extremely small, astronomers can measure it using highly sensitive telescopes. By observing this motion, scientists can detect planets that cannot be seen directly. Therefore, the concept of center of mass and conservation of linear momentum play a crucial role in discovering and studying exoplanets. So, in conclusion, this paperwork demonstrates the relationship between the center of mass and linear momentum through the formula P equal to mv and F equal to ma, proving the internal forces cannot alter a system's overall momentum. This principle allows the collective momentum of a complex system to be simplified through a single center point. Ultimately, this relationship provides physicists and engineers with a powerful tool to analyze celestial mechanics, structure, and collision without tracking individual practical trajectories. That's all from us. Thank you.